Welcome to this lecture on randomized tree construction. This is the last in our 4 lectures on alternative ways to balance information in trees. And in this lecture, we're thinking about what if you wanted to build an efficient BST, but you wanted to be lazy about it. And you don't want to write all that code for keeping it balanced because who really wants to do that? It's too much work. But suppose that you knew that you had a fixed set of data, and this is a pretty strong assumption. In other words, after you put everything into the tree, there will be no more updates to the tree, or very few, okay? So you have a fixed set of data, you want to build a binary search tree, and after you build it, pretty much nothing is going to change. Now, there are other ways we could handle this. We could sort the data, for example, but let's just pretend that we want to build a binary search tree, and we want to do so in the cheapest way possible. So the question is, what if we just built a plain or unbalanced BST? One that is a search tree, it's a binary search tree, but we don't make any effort to keep it balanced like an AVL tree or red-black tree. Well, if we did that and we're not careful, we could end up with a BST that is very imbalanced. For example, if we inserted 1, then 2, then 3, then 4, we would get a tree that looks like this, right? It would just look like a linked list. Okay. Now that is the worst case that could happen. However, what if we shuffled the data before we inserted it? And when we say we shuffle the data, we mean we take all the data that we're going to insert, and before we insert it, we shuffle its order. If we did that, it could happen that we insert that after we shuffle it, the order is still 1, 2, 3, 4. That could happen, but it's very unlikely, especially if the number of items that we have is very large. The probability of getting 1 through n in that order after shuffling, if you have a good shuffle, is 1 over n factorial. Now 1 over n factorial is vanishingly small as n gets large. I mean, if you think about it, n factorial is 1 and 2 and 6, for 1, 2, 3, 4 is 24, right? 5 is 120. So already, if you have if n is 5, the chances that you're going to get 1 through 5 after you shuffle is 1 in 120. And for 6, it's 720, right? So the chances of getting 1, 2, 3, 4, 5, 6 randomly, if you shuffle them, is 1 in 720. And that's just for 6. And now imagine 100, right? This is really 1 over n factorial is an astonishingly small number. Now, that's not the only bad sequence that we could end up with after shuffling. We could also end up with n minus 1, n minus 2 down to 3, 2, 1, right? And then we would get a tree that looks like this, right? And that would be equally, it's also a bad order, but it has equally low probability. It's also 1 over n factorial, okay? Now, out of all the ways we could shuffle our data, there are n factorial possible orderings, okay? How bad could it be if we just shuffled and picked one randomly? How likely are we to get a quote-unquote bad ordering? Well, we could prove what the answer is, but the answer really is not that likely, okay? Because these bad orderings can happen, but they are very low probability. So let's try this experiment. Rather than prove this mathematically, let's try an experiment. We're going to take the numbers 1 through 1024, and then we're going to shuffle them, and then insert them in that shuffled order into a BST, which we're not keeping balanced. And then we'll find the height of the tree. Another way of thinking of that is the depth of the deepest leaf, okay? And we won't do that once, we'll do that 100,000 times to find out how this behavior manifests itself for many different experiments. So what do you think will happen? Now, pause the video and think, what do you think is the worst thing that would happen if you did this? Insert 1024 numbers after having shuffled them. What is the worst looking tree? In other words, the tallest tree, the deepest leaf tree that you think you might observe in 100,000 experiments. Now, you might think this tree could look pretty bad, pretty unbalanced. But here's the results that I found. First of all, we can talk about the theoretical bounds on the tree height. We know that there are 1024 numbers, and the theoretical minimum height of the tree would be 10. because that's log base 2 of 1024. And of course, that would be if we somehow magically shuffled the data into an order where the first item that we insert happens to be the median item. In other words, 512. And then we somehow magically insert the first quartile and third quartile numbers here, and so on and so forth. So the perfectly balanced tree has height 10, and that's the best we can get. No tree could be shorter than that. Now, the worst case scenario is 1024, and that would be if we got a tree that looked like this, right? Or we got a tree that looked like this, and so on and so on. But also trees that look like this, like zigzag patterns, that could also be a tree of height 1024. And there are lots of these, right? And you could have zigzag patterns that look like this. So there are lots of these options for bad trees. The question is, how often do they actually come up? Well, here are the actual results over 100,000 trials, experiments. The minimum height, in other words, the best tree that I got was 16. Now 16 is not 10, but it's pretty close to 10. And it's certainly a lot better than 1024. But that's the best case. Over 100,000, you'd expect to get lucky sometimes. What about sort of looking at the worst case scenarios? Well, not the worst case, but the average case. Over all 100,000 trials, the average height of those trees was 21.1. That's pretty good. The median height was 21. And now here's the kicker. What do you think was the worst tree that I observed in 100,000 trials? The worst. Remember that the theoretical worst is 1024. How close do you think we came to that in 100,000 trials? The worst that I saw was 32. And I've run this experiment a number of times, and I hardly ever get any worse than 32 or 33. The tallest tree was 32 out of those 100,000 experiments. Okay? Now that's a long way. 32 is a long way from 1024. In fact, if you think about it, 32 is about 3 times log base 2 of 1024, which is the theoretical minimum. So we're much closer to the theoretical best than the theoretical worst. And if you think about this as this is basically order log of n, right? Because this 3 right here is nothing but a constant that you could sort of ignore. And this is log n, log of 1024. So this is essentially a pretty good result. It's actually a really good result. Here's what one of those trees looked like, okay? And I know it's hard to see because there's 1024 nodes here, but this is the root. And you can see that the deepest leaf is somewhere down here or maybe here. And it's, on the order of 20 to 30 steps away from the root. And again, this was just created by random chance. Now, here are some comments. Randomization does not guarantee a good result. It does not guarantee that the tree will be perfectly balanced or that bad inputs couldn't happen. It is possible that you could get one of these trees that looks like a linked list. But in practice, it tends to make the tree approximately balanced, and bad inputs are very, very unlikely because 1 over 1024 factorial is an amazingly small number. Calculate it. See how small it is. It's a very low chance of happening. Now, all of these experiments were based on the pretty strong assumption that we will never make changes to the tree, right? And that seems strange since we might want to do that. But perhaps if we wanted to make changes to the tree, we could batch those large changes and then use randomization to make the changes in batch. And maybe that could improve the behavior. I introduce all these ideas because randomization is not just useful here. Randomization is generally a very useful idea in algorithms and data structures for combating against worst case behaviors. And it often is a very simple tool that makes it very easy to not guarantee that the worst case won't happen, but make it very unlikely to happen.